Something just broke the rules of the solar system. A massive interstellar object just changed course. Not from gravity, not from gas, but from something we can't explain. No comet this big should move like this. Scientists are stunned. If this isn't a glitch, what force is rewriting the cosmos? A cosmic rebel crashes in on the morning of July 1st, 2025. And at 400 UTC, telescopes in Hawaii picked up something strange. A small dot was moving fast through the sky. Too fast for a normal comet. It was first spotted at a distance of 4.5 astronomical units. That's 4.5 times farther than Earth is from the Sun. Within 12 hours, observatories around the world confirmed it. This object was not from our solar system. It was moving at over 58 km/s, enough speed to escape the Sun's gravity forever. Scientists named it 3I Atlas, the third known object to fly in from another star system. Before this, we had Oumuamua in 2017 and Borisov in 2019. But this new arrival would break even more rules. Unlike Oumuamua, which was small and rocky, and Borisov, which looked like a typical comet, 3I Atlas didn't fit the pattern. Its core, called the nucleus, is between 5 and 11 km wide, making it the largest interstellar object ever seen. For comparison, Halley's Comet is only about 11 km wide and it's considered huge. Atlas also had an active coma, the glowing cloud of gas and dust that surrounds a comet. But something didn't add up. The way it moved through space didn't match the forces acting on it. Comets usually follow paths shaped by gravity, sunlight and gas jets, but this one was drifting off course. The mystery deepened when astronomers compared their predicted models with reality. What they found wasn't a small error. It was a repeating, measurable drift. Something was pushing Atlas off course, and the usual explanations weren't enough. Gravity alone couldn't explain it, and neither could sunlight or gas. When an object like a comet enters the solar system, scientists use math to predict its path. They look at its mass, speed, and how gravity from the Sun and nearby planets will pull on it. These calculations usually work very well. That's how we send spacecraft across billions of kilometers and hit tiny targets. But with 3I Atlas, something was off. Scientists ran their numbers again and again, using tools that had worked for decades. But no matter how carefully they calculated, Atlas didn't go where it was supposed to. At first, the changes were tiny. These are called residuals, small differences between where something should be and where it actually is. In most cases, these can be explained by things like gas jets on a comet's surface. But with Atlas, the differences kept growing. They weren't random either. They followed a pattern. This wasn't a mistake in measurement or a broken telescope. The object was drifting slowly, steadily, in a way that didn't match any known force. By mid-July 2025, the problem became clear. Atlas was not following the path predicted by gravity and gas alone. To find answers, scientists turned to the comet's own material. Its glowing tail, or coma, holds the key to its chemistry. By studying the gas and dust it sheds, we can learn what it's made of and what might be pushing it. But the closer we looked at Atlas's coma, the stranger the story became. When a comet gets close to the Sun, its surface begins to warm. Ice inside starts to turn into gas, creating a glowing cloud around it. This is called a coma, and it's one of the most useful things to study. The gas and dust in the coma tell scientists what the comet is made of and how much material it's losing. For 3I Atlas, the coma was bright and active, just like many comets before it. But what came next shocked astronomers. The James Webb Space Telescope locked onto Atlas and found something never seen before. Most comets in our solar system release a lot of water vapor. Some also produce carbon dioxide, CO2, but in smaller amounts, not Atlas. The readings showed that for every 1 molecule of water, there were about 8 molecules of CO2. That's an 8:1 ratio, completely backwards from what we're used to. In some cases, comets have more CO2 when they are far from the Sun. But Atlas wasn't that far. It was already within 3 AU. This high CO2 reading made it clear. Atlas was born in a very different place. It may have come from a star system where CO2 ice is more common, or from a region so cold that water stayed locked deep inside. The chemistry of the coma was already strange, but it didn't stop there. As scientists looked deeper into the light from Atlas, they found something even more unusual. Something missing. It wasn't just about what was there, but what wasn't. And what they found challenged the very building blocks of how comets form. As scientists kept watching 3I Atlas, they used powerful tools like the Very Large Telescope, VLT in Chile, to study the light coming from its coma. By breaking that light into its parts, they could see which atoms and molecules were present. This method, called spectroscopy, is like reading a chemical fingerprint. What they found next wasn't just surprising, it was confusing. The telescope showed strong signals of nickel atoms, about 4.7 x 1022 atoms per second. But something important was missing. There was no sign of iron. Normally nickel and iron appear together. They're formed in the same way in the hearts of supernovae, the giant star explosions that make heavy elements. Every comet, meteorite, and asteroid we've ever studied has both metals in similar amounts. But 3I Atlas broke that pattern. Only nickel was showing up in the data. Scientists thought maybe it was a measurement problem, but the readings were consistent across different instruments. And as the comet moved closer to the sun, the amount of nickel being released grew sharply, just like it should if sunlight was heating the surface. But even with strange chemistry and unexpected metals, there was still one big problem: motion. Atlas was drifting off course in space. Yet even with all the gas, dust, and metals it was releasing, it still shouldn't be moving this much. The force just didn't add up. So scientists looked back at the basics, how much mass this object had. And that made the mystery even deeper. If you blow on a balloon, it moves. That's the same idea scientists use to explain how comets drift. When sunlight hits a comet, it heats up. Ice inside the comet turns into gas and shoots out like a jet. This gas pushes against the comet, changing its direction slightly. We call this outgassing, and it's a well-studied process. In 2014, the Rosetta mission followed Comet 67P Churyumov-Gerasimenko, watching how gas jets changed the comet's spin and orbit. It worked perfectly for comets we understand. But 3I Atlas is in a different league. Atlas is huge. Its nucleus is between 5 and 11 kilometer wide, which means it could weigh billions of tons. That's thousands of times more massive than Oumuamua, the first interstellar visitor. To move something that heavy, you need a strong push. But the outgassing from Atlas doesn't have that kind of power. Scientists measured the dust and gas loss. The Hubble Space Telescope showed that Atlas was losing between 6 and 60 kilos of dust per second. The Swift telescope detected 40 kilos per second of water vapor. On paper, that sounds like a lot. But when you compare it to the comet's mass, it's not enough to change its path the way we're seeing. This question has been asked before. Back in 2017, a much smaller object called Oumuamua passed through the solar system. It also changed its path in a way we couldn't explain. It had no gas jets, no visible coma, just a mystery push. Now with Atlas doing something similar, but on a much bigger scale, scientists are starting to wonder, is this a pattern? Are these visitors trying to tell us something about space we don't yet understand? In October 2017, a strange object zipped through the solar system. It was named Wani Oumuamua, and it became the first confirmed visitor from another star system. It was small, about 400 meters long, but its motion caused a storm of questions. Oumuamua didn't act like a normal comet. It had no visible tail, no gas jets, and no dust cloud. But still, it moved in a way that couldn't be explained by gravity alone. It seemed to be pushed by an invisible force. At the time, some scientists said maybe it was hydrogen outgassing. Others thought it could be light pressure. But none of the ideas fully explained what was happening. Now, nearly 8 years later, we're watching 3I Atlas do something very similar, but on a much bigger scale. Atlas is about 20 times wider than Oumuamua and weighs millions of times more. If Oumuamua was a pebble, Atlas is a mountain. And yet, just like in 2017, astronomers are seeing a residual acceleration, a steady drift from where it should be based on known forces. The similarities are eerie. In both cases, scientists plugged in all the usual variables: gravity, sunlight, dust, jets, and still couldn't get the math to work. The more scientists study these mysteries, the more questions rise. Could nature really make two objects so different from what we know? Or is there a chance, however small, that these visitors weren't shaped by nature alone? One Harvard professor is asking exactly that, and his answer is sparking debate across the world. When science doesn't have answers, ideas start to stretch. That's what's happening with 3I Atlas. One of the loudest voices in the debate is Dr. Avi Loeb, a professor at Harvard University and head of the Galileo project. He made headlines in 2018 when he suggested that Oumuamua might be a piece of alien technology. Now in 2025, he's turning his attention to Atlas. In a recent post, he gave Atlas a 6 out of 10 on what he calls his Loeb scale, a rating of how likely an object is to be artificial. That's not a firm claim, but it's not a dismissal either.